Hello everyone, my name is Yusak Tanoto. I want to present my research, uh, KawanSurya, an Android-based mobile app for assessing the techno-economic potential of rooftop PV. So this is the outline of the presentation. I will give a brief introduction and then followed with methodology, and then I will explain the results and discussion, and I will present the conclusion of the research. So, as an introduction, the electricity industry is now transitioning to renewable energy technology, with renewable energy accounting for over 83% of additional capacity in 2022 worldwide, with wind and solar, including rooftop PV, accounting for 91% of the additional capacity of renewable energy. The potential for solar rooftop PV adoption is positive due to cost reductions worldwide, and particularly in Indonesia, the government aims to achieve a 23% renewable energy mix by 2025, including 3.6 gigawatt of rooftop PV. The capacity deployment requires supportive policies, comprehensive information dissemination, and also government incentives. One of the challenges to the residential rooftop PV adoption is the economic and technical barrier, primarily focusing on monetary cost and benefits, also knowledge and information aspects. So improving public knowledge and clearing up misperceptions about costly technology tariffs and policy inconsistency are among the important effort to increase rooftop PV deployment. Customers need a tool that provides an adequate system overview to assess the techno-economic potential of installing a rooftop PV. But we have limited independent application and tools are available to help customers assess the potential of solar rooftop PV in their homes. Two of the examples of this independent application are PVGIS and PVWatts calculator. They are web-based tools developed by European Commission and the National Renewable Energy Laboratory, aim to assess the performance of rooftop solar power in specific geographic region. PVGIS simulates output like yearly PV energy output, variability, and electricity cost, monthly PV energy output, and horizon outline, but does not consider user load profile. Meanwhile, PVWatts offer an optional analysis considering roof area, but does not occur for user load profile as well. We have also Solar Hub, an Indonesian rooftop PV calculator. It estimates solar PV capacity, energy generation, system cost, roof area, CO2 emission, and payback period. So this research introduces KawanSurya. It is a PV calculator, which is in English means solar friend, a free Android app for evaluating potential PV installation on grid rooftops. Here, users can select a specific location, calculate daily load profiles, measure roof area, and calculate hourly PV output power using irradiation data from the PVGIS API and homeowner's PV output equation. So here is the methodology in terms of development, navigation, and database of KawanSurya. It is an Android tool designed for data processing, calculation, and user interface component. It is built using Kotlin, the native high-level programming language for Android, and it consists of 5 main sections: electrical load, locations and area, technical parameters, economic parameters, and calculation. So also an information page and user guide are available in this app. KawanSurya app is available online and can be downloaded from the following link on Google Play Store. The PVGIS API retrieves irradiance data from 2005 to 2016 with 1 hour time step. And the tools The tool calculates energy production, generates a daily load curve, and determines the required area for rooftop PV installation. It also calculates net present value or NPV, return on investment or ROI, payback period, and cash flow. So finally, the tool displays all the results, providing a comprehensive overview of the solar PV system's potential. Figure 1 shows the Android-based user interface of KawanSurya in English and also in Bahasa Indonesia. So this is the flowchart for KawanSurya. It particularly shows stages for using the tool, which includes entering the appropriate parameters, computing inputs, and presenting outcomes. The user interface is designed with low or high fidelity wireframes to merge practical and aesthetic aspects. And it uses Room database, a library provided by Android Jetpack to process a local database. And the Room database is built on top of SQLite. And the tool has 4 distinct entities, such as task, D, PD, eco, and map. And users can specify the tables to contain data for each entity. Navigation and class diagrams depict the system structure with a class diagram of the location and area page. So figure 3 shows the KawanSurya navigation diagram. Meanwhile, figure 4 shows KawanSurya database themes. As I said before, KawanSurya consists of several pages, like features. So we have here electrical load page, which allows user to add electrical loads or appliances by clicking the add button to enter their name, amount, active power, and operational hours. The tool calculates operational hours by subtracting on time and off time. And user can input various appliances data to gather a 24-hour electrical load on their premises. And this data generates daily electrical load data and curves estimating self-consumed PV energy and excess energy sent back to the grid. The technical parameters page here, user can input various technical parameters, including installed PLN contracted power capacity, maximum rooftop PV capacity, and also PV module efficiency, nominal operating cell temperature, and temperature coefficient of power. Other parameters include tilt angle, azimuth, and annual power output reduction. KawanSurya uses the PVGIS API to obtain data from the PVGIS SARA2 dataset, which contains sun irradiance data from 2005 to 2016. The retrofit is used to create an API request with parameters like latitude, longitude, month, output, local time, global angle, aspect, and temperatures. So we can specify the PV output power, solar PV capacity, and module quantity by using this equation. So basically, rooftop PV output power is calculated using the homeowner software equation, considering factors like the rating factor and solar absorptivity and transmittance. And rooftop PV output power, the rating factor also consider panel dirt, wire loss, shadowing, snow coverage, and aging. And the tool calculates an estimate value of 0.77 to determine the impact of this parameter. The tool predicts solar PV electricity output power over multiple years, considering yearly power loss using the following equation. And the tool limits solar PV module capacity to 100% of a household contracted electricity. So we have also location and area page, also economic parameter page. The location and area page estimates the available roof area for solar PV by drawing a polygon and clicking on the areas of the house roof. And the program here used the map drawing manager library to compute the area, which is an effective usable area considering 80% of the true size of the measured polygon. An economic parameters page define the economic parameters of a rooftop PV system, including inverter price, lifetime capital cost, electricity price, feed-in tariff, annual O&M costs, and etc. And KawanSurya uses payback period to evaluate the economic feasibility of the silicon-based PV module system, also ROI and NPV. So here is the result and discussion, particularly the simulation settings and result. The case study considers low maximum power capacity scenarios and 6 policy setting scenarios. It considers also bill reduction, inflation, increased electricity tariff, and load profile. In table 4, we can see a list of appliances in a house with a 2,200 VA power contract, and the figure on the right showing the PV system, the calculated number of modules, the total capacity and required area, and also tilt angle and azimuth. And we have also here the load demand curve on the left side of the figures. The user interface result for scenario 1 for the load profile scenario and showing PV output and load profiles. Also the investment calculation is given in these figures. In simulation 1, we have 5% discount rate and 100% billing factor. And the system resulted in the total electrical load after PV installation 18.23 kilowatt hour per day or 6,659 kilowatt hour per year. PV meets a total electrical load of 1.6 kilowatt hour per day, and so on. The total electricity export also shown here. The net saving is 11,482 rupiah per day, and the discounted payback is achieved for 10.75 years at 5% discount rate, and ROI 59.21%, and NPV of 19,539,000 rupiah. We have also simulation 2, simulation 3, and simulation 4, as well as simulation 5. In simulation 2, we have used the same technical and economic parameters as simulation 1, and the payback period is 19.79% years. This is due to 65% of bill reduction factor, which reduces the power export price. And in simulation 3, we have adjusted the load profile to a constant load while maintaining the 65% bill reduction factor. The payback period is slightly higher than simulation 1, which is 11.79 years. In simulation 4, we have the quickest discounted payback period, which is 9.43 years, by assuming a 2% inflation rate. And in simulation 5, we also have a similar payback period of 9.66 years, assuming a 2% annual increase in electricity tariff and 100% export rate. So it should be noted that the payback period for PV users can be reduced by adjusting their daily electrical load profile between 7 a.m. to 5 p.m. and increasing daytime usage to lower the cost impact on billing costs by evening and nighttime loading. For the discussion, the residential customer prefer higher NPV and ROI, but decisions should also consider the ROI and NPV of different scenarios and electrical load patterns. Higher daytime energy usage is preferred for maximum electricity consumption. Load profiles and bill reduction factor influence the discounted payback period. 65% bill reduction factor and the same load profile increase the discounted payback period. Meanwhile, a 0% billing reduction factor or no compensation for selling back electricity to the grid can exceed the discounted payback period, making it advisable for rooftop PV owner to increase electrical loading during the daytime. Inflation rates in the other side can help residential project achieve shorter payback period without significantly impacting financial cash flow, and well compensation electricity export are achieved regardless of daytime usage. So KawanSurya reveals that a rooftop PV system's payback period can exceed the project lifetime due to a set of electricity bill limit, making the system uneconomical. For the conclusion, KawanSurya can be used to evaluate the techno-economic potential of installing on-grid rooftop PV under various scenarios, including daily load profiles, inflation, increased electricity tariff, and billing reduction factor. The study generated simulation results for a typical 2,200 VA household, resulting in a payback period 9.44 years or longer. While the results are influenced by electrical load profiles and bill reduction factor, incorporating inflation rate in the simulation can help recover initial investment sooner. We have also a conclusion regarding the 2% inflation rate resulted in a discounted payback period of 9.43 years, shorter than the default scenario. And further work may include studies to enhance KawanSurya capabilities and accuracy, as well as to broaden its capabilities to include off-grid and hybrid rooftop PV system and to incorporate other factors influencing the system performance. I think that's all for my presentation. Thank you very much for listening. Goodbye.